How to do a research project. Module 3, a basic statistical primer. The third module in this course is a basic statistical primer. The learning objective for this module is to choose an appropriate statistical model for the data analysis based upon study design. There are 4 types of measures of effect. 1. Absolute risk. 2. Attributable risk. 3. Population risk. And 4. Relative risk. Absolute risk is the risk of developing a disease over a time period and the odds of that happening over a stated time period. The formula for absolute risk is people who have a medical event multiplied by 100, all divided by all the people who could have the event. Attributable risk is the comparison of incidence of disease in the exposed and unexposed groups calculated by subtracting the incidence in the unexposed from the incidence in the exposed to give the excess incidence due to exposure. The formula for attributable risk is the incidence in the exposed population minus the incidence in the unexposed population. Population risk is the proportion of individuals in the general population who are affected with a particular disease. The formula for population risk is the total population affected with a disease. Relative risk is the probability or risk of developing the disease in the exposed group compared to the probability of developing the disease in the unexposed group. Note, if the population at risk decreases only marginally in both the exposed and unexposed groups, then the incident rate ratio approximates the relative risk. The formula for relative risk is the incidence in the exposed population divided by the incidence in the unexposed population. Because relative risk is also a measure of association, it is discussed at length in the following section. There are 2 main measures of association that the average physician will encounter in the majority of research studies they read or conduct. The first measure is relative risk, and the second measure is the odds ratio. To understand relative risk, one must first understand incidence, or absolute risk. Absolute risk refers to the incidence of disease in the population, while relative risk refers to the ratio of risk in the exposed population divided by the risk in the non-exposed population. Relative risk can only be calculated in the context of study designs that allow the calculation of incidence. Incidence refers to the number of new cases of a disease in a given time period divided by the population at risk for that disease at the start of that time period. Incidence can be determined from cohort studies in randomized clinical trials, but it cannot be determined from case control studies. Therefore, relative risk can only be determined from cohort studies and randomized clinical trials. Incidence cannot be calculated from a case control study because, in a case control study, the researcher does not start with a population of disease-free individuals at baseline. Instead, the researcher starts with people who already have the disease, called cases. For each case, the researcher selects 1 or more controls. Relative risk, then, is the ratio of the incidence of the disease in the exposed population divided by the incidence of the disease in the non-exposed population. Relative risk can be determined from cohort studies and randomized clinical trials. There are 3 possibilities for relative risk. 1. If the relative risk equals 1, then the risk of the disease in the exposed population is equal to the risk of the disease in the non-exposed population. There is no association between the exposure and disease. 2. If the relative risk is greater than 1, then the risk in the exposed population is greater than the risk in the non-exposed population. There is a positive association that may be causal. And 3. If the relative risk is less than 1, then the risk of the disease in the exposed population is less than the risk in the non-exposed population. There is a negative association in the exposure and it is possibly protective. The concept of the odds ratio is dependent on the concept of odds, which is defined as the ratio of the probability of a disease divided by 1 minus the probability of that disease. The odds ratio, then, refers to the odds that an exposed person develops a disease, divided by the odds that a non-exposed person develops the disease. The odds ratio can be calculated from both cohort studies and case control studies. The odds ratio is interpreted in the same manner as relative risk. A statistical hypothesis test, also called a significance test, is a procedure designed to answer the question of whether or not a null hypothesis provides a plausible explanation of the data. There are 2 types of statistical hypotheses tests that we will discuss. 1. The null hypothesis. The null hypothesis is typically the hypothesis that the data being gathered is the result of random chance, one example being a model assuming no treatment effects. Note, a significance test examines whether the null hypothesis provides a reasonable explanation of the data. And 2. The alternative hypothesis. The alternative hypothesis is typically the research hypothesis that the data being gathered is influenced by some non-random effect. one example being a model assuming that a treatment will, on average, work better than a control. Regarding the null hypothesis, a test statistic is a measure of the difference between the data observed and what is expected when the null hypothesis is true. Commonly used test statistics include the t-statistic associated with the student's t-test, the chi-square statistic associated with the chi-square test, and the f-statistic associated with the analysis of variance, or ANOVA, test. When conducting a statistical hypothesis test, the following describes the steps used. 1. Formulate null and alternative hypotheses. 2. Calculate a test statistic. The test statistic is used to measure or represent the difference between the data collected and the data that would be expected if the null hypothesis were true. 3. Compare the calculated test statistic to a predetermined value to determine whether the null hypothesis will be rejected or not rejected. That predetermined value, in turn, is based on the amount of error tolerated in decision-making. And 4. If the calculated test statistic is greater than the allowed value, then the null hypothesis is rejected. If the calculated test statistic is lesser, then the null hypothesis is not rejected. There are two types of error that are significant when hypothesis testing: Type 1 and Type 2. Type 1 error: the probability of incorrectly rejecting the null hypothesis when it is true. There is no standard rule for the Type 1 error. The Type 1 error rate is set by the investigator based on the consequences of falsely rejecting the null hypothesis. The most level set for the Type 1 error rate is 5%, or 0.05. Type 2 error: the failure to reject a null hypothesis that is false. The Type 2 error rate is based on the power of the study, which, in turn, is directly related to the sample size. The following table describes the error types. There are two ways of quantifying statistical significance. One is the p-value and the other is the confidence interval. The p-value is one of the most misunderstood and misused concepts in statistics. In simple terms, the p-value represents the probability that the data will be observed, along with the calculated test statistic, given that the null hypothesis was true. The p-value does not denote clinical significance. It only denotes statistical significance. When conducting a statistical hypothesis test, the researcher is calculating a test statistic and compares that test statistic to a predetermined value. One will note that the formulae for the common test statistics all contain the sample size, so no matter what the statistic is, whether t-statistic or f-statistic, etc., the larger the sample size, the larger the absolute magnitude of the test statistic, and the greater the likelihood it will exceed the predetermined value that represents the threshold for rejecting the null hypothesis. We will now examine an example of the p-value. In this example, imagine that a researcher is interested in studying mathematics test scores between School A and School B. 1. Assume that the researcher believes that the truth is that students from School A are no better at mathematics than students from School B. 2. The researcher then administers a math test, maximum points 100, to a sample of students from both schools, ensuring that the students in the sample are of the same age and had the same grades over the past 2 years. 3. The null hypothesis, based on the belief of the truth, would be that the mean math test scores of students from each school would be no different. 4. The researcher then calculates the average score for each school and notes that the mean score for School A is 30 points higher than the mean for School B. At this point, what is the probability that if students from School A and B are truly equal at taking a math test, that the researcher would be able to take a sample of those students and find mean test scores that are as extreme as what is observed? Without doing any formal calculations, it is clear that the probability would be low. If the truth is that the two groups of students are equal at math, it is unlikely that the researcher could take a large sample from each school and end up with mean math test scores as different as what was observed, 30 points on a 100-point scale. 5. This probability represents the p-value. In this example, the p-value would almost certainly end up being very low, most likely less than 0.05. And 6. Consequently, the researcher would reject the null hypothesis. To put it simply, no matter how small the difference is between two groups, the p-value can be progressively lowered by increasing the sample size. Almost any difference can be made statistically significant if the sample size is large enough. Information from the references below were used for this section on p-values. The second way to quantify statistical significance is the confidence interval. The confidence interval is defined as the X% confidence interval around a parameter, such as a mean or proportion, that is an interval constructed in such a way that there is an X% probability that it contains the true population value for that parameter. However, a confidence interval is typically constructed in the same way no matter what, for it equals the sample parameter plus or minus the multiplier, multiplied by the standard error of parameter. The multiplier used is a direct function of the level of the confidence interval. If the researcher is constructing a 95% confidence interval, the multiplier will be larger than a 90% confidence interval. Thus, the standard error is inversely proportional to the sample size. The larger the sample size, the smaller the standard error and the narrower the confidence interval. In the next example, we will examine how the confidence interval is used. 1. The researcher typically takes a sample. 2. From that sample, the researcher calculates the mean or proportion by calculating the odds ratios or relative risks. 3. Imagine the researcher repeated the sampling procedure 100 times and that each time the researcher obtained a sample, they constructed an interval around the sample parameter of interest. What percent of those 100 intervals would contain the true value of the population parameter the researcher is estimating? And 4. Answering this question is the purpose of the confidence interval because it is an interval surrounding a parameter, obtained from a sample, such that the probability that the interval contains the true population value for that parameter is X%. Conceptually, there is a two-step process to carrying out studies and evaluating evidence. 1. Determine whether there is an association and that the association is real and not spurious. And 2. Determine whether that association is likely to be causal. There are several guidelines to help determine whether an observed association is causal. 1. The temporal relationship between exposure and disease. 2. The stronger the association, i.e. the higher the relative risk, the more likely the relationship is causal. Note, the presence of a dose-response relationship is strong evidence for a causal association. 3. Findings are replicable. 4. Biologic plausibility. 5. Risk of disease is reduced when exposure to the factor in question is reduced. And 6. Association is consistent with other knowledge. Research studies that aim to find an association between an exposure and an outcome can be done in one of two ways. In one category are studies with only one outcome measure per person or subject, which we now will discuss. In the following example, if a researcher were examining the effect of drug A on achieving a cure for disease A, the researcher would do the following. 1. Sample N individuals from a population of people at risk for disease A. 2. Assign half the sample to get drug A and half to get a placebo. And 3. Ascertain disease status once for each patient. In this study example where each individual had the outcome measured or assessed on them just once, the outcome measurement on each participant is independent of the outcome measurement on each of the other participants. Consequently, the researcher could use classic statistical tests such as 1. The student's t-test, 2. The analysis of variance test, or ANOVA, or 3. The chi-square test. The researcher could also use classic regression techniques, such as linear regression and logistic regression. Now we will examine the second way to find an association between an exposure and an outcome. In this scenario, imagine a researcher is conducting a study of the effect of drug B on thyroid-stimulating hormone, or TSH, levels. The hypothesis is that drug B will reduce TSH levels. Instead of having two groups, one getting drug B and one getting a placebo, measuring TSH levels once for each patient in each of the two groups and then comparing the average, let us imagine the researcher decides instead to use each person as their own control, measure TSH at baseline, and then give everyone drug B followed by repeat measurement of TSH. In this example, the researcher has measured the outcome 2 times on each patient, and outcome measurements on the same individual are going to tend to be correlated. Classic statistical tests such as the t-test and the chi-square test require the observations to be independent. If the assumption of independence is violated and the researcher uses these tests, they will get invalid or misleading results. Specifically, the chances of the researcher incorrectly rejecting the null hypothesis will be increased. In this second example, the researcher's observations are correlated and, consequently, the researcher would need to use different statistical methods to test the hypotheses. Examples of appropriate methods include the paired t-test, repeated measures of ANOVA, and hierarchical or multi-level regression modeling. Note: an in-depth discussion of these advanced methods is beyond the scope of this course, but these are important methods to know. The main point throughout these examples is that when a researcher measures an outcome multiple times on each study subject, the researcher will have a correlated data structure and cannot use the typical statistical models that most novice researchers are familiar with, because these typical statistical tests are all based on the assumption of independent observations. Now we will look at an example that explores multiple comparisons. For the following example, imagine a researcher is comparing two groups on their performance on a math test. The hypothesis is that Group A is more proficient at math than Group B. The researcher gives the two groups a test consisting of algebra, calculus, arithmetic, and geometry. Instead of comparing the composite score, the researcher compares the subscores and conducts 4 statistical tests to test the overall hypothesis. This example describes the multiple comparison scenario. The more statistical tests the researcher conducts, the more likely at least one will be statistically significant according to the laws of chance. More specifically, in this scenario, the probability of a type 1 error is increased. Type 1 error refers to the probability of rejecting the null hypothesis when it is true, as previously discussed. When a researcher has a multiple comparison scenario, the researcher must use a stricter standard to define statistical significance for each individual test so that the overall type 1 error remains at the standard 0.05. One classic way to adjust the significance level for each individual test is to divide the desired overall significance level, usually 0.05, by the number of statistical tests conducted. In the previous example, with 4 statistical tests, the new significance level for each individual test would be 0.05 divided by 4, or 0.0125. So, for each of the 4 individual tests, the researcher would not conclude statistical significance unless the p-value was less than 0.0125. Overall, it is extremely important to understand the implications of statistical analysis choices and to choose the correct kind of statistical analysis based upon study design. The next section in this course is Module 4, Internal Validity and Bias. The learning objective for this module is to describe how to distinguish between internal and external validity and types of bias.